reactivity trends in the metals. Yeah. Your first question was, for example, lithium to potassium. All right.
Yeah.
As we've already mentioned, okay, the first principle to remember is that metals react by losing electrons. I'll use short form. So it follows logically that the easier it is to lose the electrons, the more reactive something is. Yeah? Simple principle that we've already talked about. The
Yeah.
next bit, therefore, is what decides whether it's easy or not to lose electrons. Yeah? And that's the bit that we're going to talk about, what I was talking about earlier on. So let's take a look at a lithium ion. Okay, so if you have a lithium one, you've got that, and oh, that's not going to work. Apologies. Sort of like that. It's a bit lopsided. But what lithium has is two electrons in its inner ring, inner shell, and one electron on the outer shell, because it's in group 1. All right? Now, if we look at the same concept for potassium, let me just complete that. So far, that's 2 in the inner shell, the innermost shell, 8 in that next shell, all right? And then it's got another 8, all right? What's the atomic number of potassium on your periodic table? Take a look.
19.
Exactly, right? So if you look at potassium here, you've got, that's the same number of electrons as protons. The atomic number also tells you the number of electrons in the atom itself. So you've got 2 and 8, that's 10. And then another 8 is 18. So one more shell. Oops, I hope this is okay. Just about do it. And there. All right. So look, what it's going to do, in order to react, okay, because these are group 1s, they want to lose that outer electron. Okay. So group 1s. All right. So the outer electron needs to be lost, gotten rid of, in order for them to react. Now, the explanation to the point you're making, just to recap on what we were talking about earlier, you see the distance from the center to the electron, all right? That's referred to as the atomic radius. You may not have used that phrase in lessons in school, right? They might not have said that. Don't worry about that. All you need to remember is that is the distance from nucleus to the outer electron. Okay? In potassium, can you see how that distance is that much more? Yeah?
Yeah.
The outer electron is much further away. And this is what gives you the trend in reactivity. All right? So, in effect, the important part, the outer electron is further away from nucleus. Okay, that's point one. Two, so electrostatic force between positive nucleus and negative electrons is weaker in potassium than in lithium. Okay? Therefore, right, potassium can lose its electrons more easily than lithium, all right? And that is the crux of it. Okay.
Okay.
Therefore, potassium is more reactive than lithium. All right. And the question was, how do you use that relationship to predict other metal reactivities? Right. So I'll come on to that in just a moment. One other thing that you may not have done yet in school, but it's not just the distance. Okay. One other thing, which is a little bit more advanced for you, but it's worth mentioning it if you ever use this to revise later on. You see, between the outer electrons to the nucleus in lithium, there aren't many other electrons. There's only the two in the inner shell, right? Okay.
Yeah.
In potassium, you've got 8 in that inner shell, so the one there, and then you've got another 8 in that second shell there, and then the 2 original in the inner. So you've got many, many more electrons between the outer one and the nucleus, right? So another factor, not just the distance, but also to mention, there are more inner electrons causes, oops, oh, sorry, outer electron to be repelled. Do you remember that from physics?
Yeah.
All right. So it's called a double effect. Meaning you've got the radius, right? Greater radius, and push from inner electrons. So both of those effects, right, make the outer electron easier to lose in potassium. So the bigger the atom, as you go down a group, right, the bigger the atom, the easier it is to lose the outer electrons, right, because it's further away from the nucleus and you've got many, many more inner electrons pushing that outer electron further away. All right? In other words, interfering so the nucleus can't pull on it as tightly. So does that trend make sense? Yeah?
Yeah.
And so this whole thing, right? So this is as you go down periodic table. Let me just do a little rough sketch. However many, I'm not doing an exact number, right? It'll do. So you've got groups 1, 2, 3, 4, 5, 6, and 7. We're probably not too interested in the noble gases because they're not reactive anyway. All right. But if we go down like that, basically, all right. So you've got lithium there, sodium there, potassium, beryllium. What's the one under beryllium? Do you remember? Oh, don't cheat. Go on.
Magnesium.
Magnesium, yes. All right. Then you got calcium, etc. Okay, so they go down the group that way. Group 3, you've got boron, aluminium, and so on. Okay, so those are the main metallic groups that you'd need to talk about as far as the trends go. All right. Okay, hang on a second. What do you got here? Okay. All right, so there's your schematic periodic table, very simply put. All right. So what this is telling you is that from the trends we've just talked about, as you go down a metallic group, like group 1, for example, it goes from less reactive to more reactive. All right? So in any metallic group, so same applies for group 2 as well. All right? So you can use the same explanation, the same points, and especially this double effect thing that I was talking about. All right? And that would also explain the trend from, let's say, beryllium to magnesium to calcium. It's exactly the same reasons. They get more reactive as you go down because the atoms are getting bigger and they have more electrons overall. All right. Same here. I mean, boron doesn't behave entirely as a metal. Remember here, you've got the little steps for the metal non-metal split, right? Like that. So everything here is metallic. And the middle bit, by the way, we're not talking about because those are transition metals. So these are all metals all the way along here. Everything in this side of the periodic table. Only the top right corner above those blue steps, right? These are non-metals. And their trends are a little different. Okay. So are you okay with the explanation going from lithium to potassium and using that as a guidance? Does that make sense so far?
Yeah.
Yeah? All right, cool. So got that. The next thing that you asked in that message was the difference between reactions of metals with air and water provide evidence for the trend in reactivity of group 1. Okay, so let's talk about that. All right. Group 1, particularly. All right. We already know that lithium, sodium, and potassium, right? Those are the main three that you usually talk about. And we know that they get more reactive as you go down. All right. All right. So explaining that trend in terms of the reactivity, now we want to talk about air and water. All right. Caitlin, do you remember anything in terms of what happens to them? For example, if you put lithium in air, and you know what, let me just restructure that. In air and in water, do you remember at all what happens?
No.
Okay. In many cases, when you put a metal plus air, right, often they become either dull or another word for it is tarnish. Okay. You could even have, like with iron, you can have rusting as well, but that needs water as well. All right. Okay. So the point is, lithium in air, it's not going to do too much. All right. Because it is not that reactive. All right. So, you know, this thing about rust, for example, you can say the whole thing corrodes. All right. And all of these things. The point is that lithium on its own, without any kind of, let's say, fire or something else, right? It's a very slow reaction. All right. Sodium in air, right, will tarnish very quickly. Fast rather than faster. Okay? And potassium is even faster than that. All right. So, potassium in air, looking at the same kind of trend, all right? Any idea? Do you remember anything about it? No? All right. It reacts, this is the way we should say it, I suppose. These ones are more violent. So this one I'll say violent even. Meaning it ignites. All right? It basically starts burning on its own. Okay, so with potassium, ignites and burns in air violently. All right? Whereas lithium is much more of a slow reaction. It can still ignite, but it's much slower. All right? That, as far as the air goes, shows how the metals are getting more reactive as you go down the group of group one. All right? And as a result, do you remember at all, have they told you in school, how sodium and potassium are stored?
No.
No? They're actually stored in oil. Why do we do that?
Because it will react with water.
And air.
Uh,
If you just have it open to the air, the stuff will just react and start burning. Okay? And that effectively is a trend that you need to talk about. Now, talking about the water bit, all right, lithium again is slow, all right. Sodium is, it fizzes, all right, and can sometimes like actually give you a flame, right? Sometimes, but usually it fizzes, it whizzes around the surface. So if you take a small piece of sodium and put it in some water, you'll find that it whizzes around, giving off gas, right? And it fizzes while it's doing that. Okay. Potassium will not only fizz, but you'll get a flame as well. It is so reactive, it reacts with the water so powerfully, violently even, yeah, that it can start a fire, like a flame, and it can actually explode on the water. That's how powerfully reactive sodium is compared to the other two. All right, and the reaction of them. I'll just put the reaction thing in here for you. 1 second. So first of all, the reaction with air. So let's take an example. You've got lithium plus oxygen. So it's not air, it's the actual oxygen in the air that the reaction happens with. All right? And they produce an oxide. Lithium 2 oxide, right? So Li2O. All right? And therefore, for each oxygen, you need 2 lithiums because it's group 1 and then oxygen has 2 bonds. So effectively, you're going to need 4 of those, 2 of those. Does that make sense? All right, so lithium, sorry, go on.
Yeah, but explain, I don't understand.
Which bit?
Why there's 4 in front of the Li.
All right, because for each oxygen, right here, right, remember oxygen is diatomic, so it comes in a molecule of 2 oxygens.
Yeah.
All right, each of the oxygen atoms needs 2 lithiums because lithium is in group 1.
Yeah.
All right, so if I have 2 oxygen atoms, then I'm going to need double the number of lithium, so it's 4. So if you look on the right hand side now, all the numbers balance. So I've got 2 times 2 lithiums, so 4 lithiums, and I've got 2 oxygens. Does that make sense?
Yeah.
Yeah? All right. So that basically is the reaction with oxygen. And you substitute any of the group 1s, it'll be the same thing. All right? It'll be 4 sodiums plus O2 will be 2 Na2. So I could just write that down. That, all right? Or etc. So all the group 1s will form that kind of an oxide. All right. So the word equation is group 1. Let's put that in. Group 1 metal plus oxygen goes to metal oxide. All right. So that is the reaction that you need to know for air. All right. And as I said, I've put in kind of slow, fast, faster, that sort of thing. Lithium still does react, but not as fast as sodium or potassium, as in that table. All right. Lithium will react, maybe not so slow, but definitely not as fast as or violently as sodium and potassium. Okay. You will still get fizzing, so call it a slow fizz. All right, and heat is given off. Okay, now let's do the water reaction. So any of the group 1s with water. So imagine you've got again lithium. All right, so you've got Li plus H2O, and what it produces is an alkali solution made up of lithium hydroxide. Okay. In this case, remember that the hydroxide ion, OH, all right, has a -1 charge. And lithium, when it bonds, it makes a +1 ion, right? So it's just 1 to 1. So this one's a +1, this one's a -1, so they balance each other. Okay, so you don't need more than that. And now to balance, excuse me, balance this equation, the other product, the fizzing, right, is caused by hydrogen gas. I'll put in a state symbol there, just to show that that is what causes the fizzing. Okay, if I need to balance this whole thing, all right, I now need 2 of them, okay, 2 of them and 2 of them. because hydrogen is a diatomic, and so I need to double everything up to make sure I've got H2 at the end. Okay, does that make sense? And
Yeah.
it's the hydroxide, the metal hydroxide, that's alkali. It's an alkali, or you can call it an alkaline solution that's left over, because this will be aqueous. All right? The lithium hydroxide dissolves in the water. So the general equation, the word equation, is again group 1 metal plus water goes to a metal, metal hydroxide plus hydrogen gas. And it's, as I said earlier, it's the hydrogen gas being given off that creates the fizzing. That's the effect of the fizzing. All right?
Yeah.
Okay, so that's the water part. So that's the air and the water done, and let's just go to the acid reaction. So metal plus acid. So again, using lithium as an example, right? Lithium plus hydrochloric acid, all right? And in this case, lithium is going to be a solid. I'm just putting the state symbols in case you need them later. Hydrochloric acid, dilute, all right? Is aqueous, so it's dissolved in water. What that does, it produces a metal salt, all right? Lithium chloride, which again is aqueous because it's soluble, so it dissolves into the water, and it gives off hydrogen gas again. All right, so fizzing. Again, to balance the equation, all right, we need two of those, and two of those. Okay, that balances it. The general form is effectively metal plus acid. Do you know what the lithium chloride is called? The result of a reaction between a metal and an acid. Do you remember any of that? No?
Not salt.
Yes, it is. Well done. Well done. So it's a metal salt. I don't really need to write metal salt, but let's write it's the salt from that particular metal. All right? Plus hydrogen gas. Okay? And so that is your general reaction. All right? I'll do the other one with a sulfate, sulfuric acid, just to give you an example. So if we're dealing with potassium now, let's use sodium. We haven't used sodium much. Sodium plus the formula for sulfuric acid, in case you've forgotten it, is H2SO4. All right? Again, aqueous, and sodium will be a solid. And that again will produce the salt, right? So it'll be sodium Na2SO4. Okay? That'll be aqueous because it dissolves in the water, and then the hydrogen gas as before. All right? Notice the important thing about the salt, right? Just a little bit of side learning. The salt is always made up of the metal and the negative ion in the acid. So in this case, it's the chlorine, right? In the sulfate, in this example, it's the sodium is the metal and the sulfate, all right? And that's what combines to give you the salt in each case. And the hydrogen is what's given off, all right? Does that make sense?
is Na2?
Because that's what I was just about to come on to. Whilst we're doing this, let's do the common acids. So you've got HCl, all right, which the Cl in there is a Cl minus, all right, so it only has a single negative charge. So it makes one bond. I know people are going to comment about that, and it's not quite as simple as that, but as far as you're concerned, that's all you need. It makes one bond. That's why with lithium, which also makes just one bond, you only need one of each. So it's just lithium chloride, LiCl. All right? If I have another one, this one wasn't in your notes, but nitric acid, all right? Then the ion from that forms the salt, is NO3 minus. Okay, you are expected to know these. All right. So that bond is like one bond again, all right? And the other one, H2SO4, is a sulfate. Now the sulfate has a 2 minus charge on it. Okay? So it effectively forms two bonds. Okay. So let's just put the thing. So hydrochloric acid. Hydrochloric. This one's nitric. And then sulfuric. So these are all your acids. All right. These ions on the right hand side you're seeing there, that'll be referred to, okay, as chloride, nitrate, and sulfate. So that's how to name the salts that are produced. Does that all make sense so far?
Yeah.
Yeah? Okay. Now, after all of that, the point of looking at the acids is that when you put these metals, or group 1 metals and whatever, with an acid, right, the speed of the reaction with acid determines, again, how reactive the metal is. All right? And just want to bring up this table for you. 1 second. Yeah, okay. So, very quick summary now. All right. The most reactive all over that lot is potassium. All right. So when you put put in red. Yeah, that's fine. Potassium, sodium, lithium in that order, the ones that you're going to be dealing with, those are the most reactive, like getting less reactive as you go down. Those ones plus acid, all right, dilute acid, they give you an explosion basically. All right, so they're all very reactive. Okay, the one with the water, as I said to you, the reaction speeds up as you go from lithium to potassium. Okay, you know what? I'm going to reverse my decision there. I'm going to change that. I don't want to confuse you. Let's put it back to the way we have it in the periodic table. My apologies to anybody else who might be watching this. Okay, so we're doing that. And it's more reactive as you go down. Gets more reactive going down the group. Okay, so combination of looking at their reactions with water, which was just above it. Remember what I put in the table there. All right, so you have the air and you've got the water reactions. I've tried to simplify it a little, yeah, With lithium, it's not quite as slow as the word slow might imply, but compared to sodium and potassium, it's definitely a little slower. All right, and maybe a little less fizzing, a slightly slower fizzing than you would in terms of the water reaction. Okay, so all of these things, these trends put together, and being able to put these reactions together in a test or a question that you have, you can use these and the nature of the reactions to show which ones are more reactive and which ones are less. All right. Again, with this one, with potassium, it's a violent explosion. Okay, if you put a lump of potassium into an acid, and normally you wouldn't. Okay. Lithium, again, it explodes, but not so violently. That's the difference between them. All right.
Okay.
Okay. Have we addressed the three different conditions that you had? Yeah?
Yeah.
All right. Any other questions on that at all?
No.
No? All right, then let's finish there on that particular topic.